This afternoon I'm going to talk about some of our pork board funded research. And we did all this work in grow finisher pigs. We haven't done anything with the sow or anything really with nursery pigs. And this is a project. I'm not going to go through the introduction on PRRS, you already know enough about it. But really this is a project that we're really trying to understand how to feed a sick pig. Because what we know is that if we have a disease or inflammatory challenge, we have a stress response or immune challenge response, we have a loss of amino acids and a metabolic shift that may occur, we have a depressed anabolic signaling that can occur in our grow finisher pigs, and all this is going to really lead to reduced growth potential and increased metabolic demand and have an impact on our feed efficiency. So, as Fitz said, there was a group of us got together and actually wrote some stuff down to put in a pork board proposal. There were many other people involved with the initial think tank, but this is just a group of us that put an idea on paper. So I would say if you've got a good idea to do research, if you put it on paper and you submit it to the pork board, it's got a chance of getting funded. If you don't write it down, then they can't fund it. Because there was many people that contributed to this, but they just didn't want to write anything. So we, a group of nutritionists, vets, geneticists, etc. from multiple universities that all contributed to this research. So it's not just myself doing all the work, it was a group effort. And these are some of the questions that we really wanted to address. Is how does an immune challenge alter feed intake and digestibility in these grow finisher pigs? And particularly, we want to look at this in the face of a PRRS. And then does an immune challenge, or does a PRRS challenge, how does it actually alter tissue accretion? So do we have an impact on lean accretion more so than adipose or fat accretion or bone accretion? So what does longitudinally, what does this look like? More importantly, there's not a lot of accurate feed efficiency data out there with regard to disease challenges out in the field. So we really want to look at the impact of PRRS on feed efficiency. And then ultimately what we want to get to, and then the 2012 NRC really highlighted this, we do not really have a good handle on what the nutrition requirements are for sick pigs or poor health pigs. So hopefully we can start to generate some information that can help us address this nutritional requirements. And then ultimately, if this is for the producer, how do we best manage and feed these sick pigs? So these are kind of the overall questions that we want to address over the next couple of years. And I also challenge the industry as a whole, we should be addressing these type of questions. So really the objective of this study that I'm going to present today was really to characterize in a grow finish pig the impact of PRRS, what does it do to feed efficiency, what's its effect on body composition, nutrient digestibility, tissue accretion, and also some post-absorptive metabolism. Because if we understand what is the impact of the disease on the pig and what is the timing of the impact, therefore it's going to help us better go in with mitigation strategies. So our general hypothesis was that PRRS will cause a reduction in growth rates. Yes, we know that already. But then this is going to be associated with a decrease in energy and nutrient digestibility. And furthermore, this will translate to a reduction in lean growth potential and lean growth accretion, but not bone and also not fat so much. So the methods that we used for this study, we had 60 choice genetic maternal line gilts. They started off at around 75 pounds of body weight. They were litter mates, and what we did, we split a gilt from each litter to 2 different sites. And so we had 30 litter mate pairs that we split across a clean site and we'll call it a dirty site, or a PRRS negative, a PRRS positive site. We grouped these pigs in 5 pens of 6 pigs per pen. There's a representation of the pen structure up here. And one of the sites we inoculated the pigs with an intramuscular injection of PRRS virus. And this was a field strain that was isolated just from about half a mile down the road from where this barn's located at Stanhope, Iowa. And then our control or naive pigs actually received an intramuscular injection of saline as a mock vehicle challenge. Then over the production period of about 115 days, we measured performance, tissue accretion, digestibility, PRRS titers, etc. So if you want to look at this in a flow chart or in a diagram, We have PRRS naive pigs coming from a naive herd. At about 75 pounds, we did an initial body composition analysis on these pigs, and I'll explain this shortly. We split them across 2 barns. Then we actually challenged the pigs. Over a 42-day period, we looked at performance, body composition, titers. Then again, we looked at body composition 35 days later, and this is really to look at period 2 to see if there was any compensatory growth going on. And then finally, these pigs went to market at approximately 115 days. So that's kind of the general structure of our project. They were fed a 4 phases diet, and then it's just a typical Midwest diet, about 20% DDG, soybean meal, corn, etc. Nothing fancy. But we also put titanium dioxide in the diet, and that's a digestible or non-digestible marker, because we actually took fecal grab samples at 2 time points throughout the study to look at total tract digestibility in these pigs. So what does the PRRS titers look like? All pigs were negative when they came in for PCR. By week 1, they were all PCR positive up to week 5 or up to week 3. Week 5, they had seroconverted. As we can see here, they're starting to seroconvert down with our EIA data. And then by week 10, they've actually not shed any live virus, but they've all seroconverted. And our naive pigs actually stayed naive for the whole period. And this is typical from a Iowa pork producer funded project using this same virus, of which we saw pigs actually were positive and they seroconverted by about 14 to 28 days. So what does the body weights look like? So we started off with pigs that are around 75 pounds, 36 kilos. And then the black line here is our PRRS naive pigs. The red one is our PRRS positive pigs. And what we see over about 15 to 18 weeks, it took us about 14 extra days to get our PRRS positive pigs to market, or to the same body weight, I should say, or about 280, 285 pounds. So this initial PRRS challenge set these pigs back about 14 days. And by design, we wanted to get to the pigs to the same live body weight, instead of just going out the same days of age, or days post-inoculation. So the overall growth performance for this study, so this is about 105 days for our naive pigs, 119 days for our positive pigs. We see about a 6% reduction in feed intake, 10% in average daily gain due to PRRS inoculation compared to our naive pigs. We had about a 7% difference or reduction in feed efficiency, in gain to feed, and this also correlated to about 6% with carcass feed efficiency if we express it on a carcass basis. So over the whole period, we're actually taking a nice hit with regard to feed efficiency as well as overall performance. So this is a graph that I really like. What I did is actually block this into within periods. So this is within the first week, within the second week, third week, fourth week, etc. And this shows the within week variation or changes in average daily gain up the top and average daily feed intake. And what we see here is really the first 4 to 5 weeks, we're really taking a big hit with regard to average daily gain, up to 50% reduction, and feed efficiency is about 32% reduction. But by about weeks 5 or 6, the actual performance of these two groups of pigs come back together. So we seem to be doing a lot of damage actually in the first 4 weeks post-inoculation. And this could have big implications if we're talking about mitigation strategies. And then we have about a 25 to 27% reduction in feed efficiency due to PRRS inoculation, and pretty much feed efficiency comes back together by about week 5, week 6 for our two groups of pigs. And so we don't see any statistical differences after week 5 with regard to feed efficiency. So we know we've got general gross performance differences, but are we impacting body composition and, more importantly, tissue accretion? Is the reductions the same? So what we've been doing at Iowa State over the last 4 years, we've been using a dual X-ray absorptiometry machine to actually look at body composition longitudinally in our pigs. And this gets away from a serial slaughter technique where we can actually look at the same pig across time. So this is one of our pigs here. We can sedate the pig, we can scan it as many times as iCuck would allow us. And then what we can do, we can get a total mass, DEXA predicted lean, fat percentage, and bone mineral density and content. A lot of you may be familiar with this actual technology, more to do with bone health and bone density. We can actually use it for body composition. But what we've been doing over the last 4 or 5 years, actually I've been building some internal regression curves to actually correct for gut fill, bladder fill, etc. And I'd like to show this to everyone to show how good this is DEXA predicted lean. If you took the top left panel, DEXA predicted lean on the x-axis, and chemical protein once we've stripped out the pigs, ground them up. This is whole body basis. We get a really nice linear regression. So whole body lean to protein. This thing's going flat. Also we see a nice regression for lean, DEXA lean versus chemical lean, ASH, a little bit more variability. Whole body fat, we get a nice linear regression. So therefore we can grab our raw DEXA data and actually put it through these regressions to correct for gut fill, bladder fill. And so we're really looking truly at a whole body composition and not luminal contents, etc. So this is typical for what we saw at about 80 days when we did this will be our second scan, our third scan, our last scan. Our PRRS naive pigs were about 99 kilograms in body weight. There's about 9 kilograms, this is 99 kilograms. There's about 9 kilogram difference between our PRRS positive pigs. And again, we can actually grab this data, look at it across time, and then divide it by the amount of days to look at tissue accretion. So what are we doing to tissue accretion? We know we're affecting whole body, but what about accretion rates? So in this table here, we look at our first 42 days, so the first 6 weeks versus the second 35-day period over here. And we can see we take about 130, 140 gram hit on lean due to PRRS inoculation. That translates to about 30 grams in protein, about a 40 gram reduction in fat deposition per day. Bone mineral content due to PRRS also goes down, and our total body or whole body growth rates also go down. And these numbers here are pretty close to what we got from our scale data. But if you notice in our second period, so the next 35 days from day 42 to day 80 post-inoculation, we see equal growth performance in our pigs. In other words, tissue accretion rates come back together and there's no statistical difference except for in fat. So if we look at the overall period over the whole 80 days when we did the scans, really the damage has been done in the first 4 to 6 weeks. That's really having a big impact on tissue accretion. So these pigs are just never catching up. So it raises a question about compensatory growth. Does it exist or not? In this data set, you could argue it doesn't exist because we didn't see it in our second period. So we saw no compensatory growth here. So pigs rebounded after about 6 weeks. So this is some of the interesting data. What is the impact on total tract digestibility? If you remember, I said we put titanium dioxide into the diets. And what we did over a 3-day period during the middle of this first kind of collection period and also in the middle of this second collection period for body composition, we took 3 days worth of individual pig total tract fecal grab samples, pulled them together within a pig, dried them, ground them up and did proximates. So we looked at nitrogen, dry matter, energy, and as well as titanium dioxide. And what we wanted to do is get an idea of what was going on with total tract apparent digestibility in the middle of these 2 periods, and does it explain differences regarding some of our tissue accretion and growth performance data. So if you look at, this is the 21-day data. If you look in that middle of that first period, we can see we're taking about a 4 to 5% hit on total tract digestibility coefficients for dry matter digestibility, nitrogen digestibility, and total energy digestibility. This is coupled with reduced feed intake. And so overall, this is going to help contribute to some of the poorer growth performances that we're seeing. But when we look at 65 days, when we collected samples, so this is during the middle of our second collection period, we're still taking a 1 to 3% hit in our total tract digestibility. Even though we've got feed intake is similar between our two treatment groups at this stage. So there appears to be a long-lasting effect on total tract digestibility within these pigs. And so this is just another way of looking at it. If these are just percentage differences between coefficients of the PRRS positive and PRRS naive pigs, so there's a 3% difference between our pigs with regard to dry matter digestibility in the first period. In the second period, that halves to about 2%. Nitrogen halves to about 2.5% from 5.5%. So it's got this carryover effect, which is really intriguing because no one's really seen this before or actually reported it from what I can see in the literature. So when we look at the overall performance, what does it mean for carcass performance and the bottom line? And part of the mandate from the pork board has been to put some economic analysis to some of the data that we're getting. So we've got a nice data set where we've got the actual production data. I've also got some molecular data, but more importantly, I've been challenged to make this industry applicable, and so we did an economic analysis on this work, and I'll present that in the next couple of slides. But overall, this is the N of 30 in both of these. Our live weights were slightly heavier with our PRRS positive pigs because it probably took about 12 days to get them extra to get them to the same live weight that we had to fit into a plant schedule. Carcass weight was identical between the two, and we saw a reduction, a 1% reduction in yield due to the PRRS inoculation. As based off our DEXA data, we saw a nice reduction in back fat, and also due to the fact of our yields and the bigger live weight in carcass, we saw an increase in lean tissue percentage due to PRRS inoculation in our pigs, taken to the same live weight. So, challenge me on this if you wish, but these are a lot of assumptions. Anytime you do an economic analysis, we assume a lot of things, and see that these are my assumptions. So if we look at, this is assumption if taken to the same live weight in the top table, and the bottom table, assumption if taken to the same age or days of challenge. So up here, this is our overall feed intake. Our PRRS positive pigs were in the barn for an extra 14 days, therefore overall feed intake, daily feed intake was also different. Total amount of feed they ate was about 31 more pounds. If you have $350 a tonne for feed as an assumption, these pigs would have eaten about $5.40 more. Due to the extra barn cost to housing these pigs, $1.40, we had an increase in carcass weight, 2 pounds or heavier. Therefore, a carcass value, if you standardised to a base price, was around 66 cents. So overall, by taking the pigs an extra 14 days, we estimated in this system under our data, it cost us $6.14 this PRRS challenge. If we had to get the pigs all out at the same time, in other words, we take it to the same days, so the assumption would be around that 105, 106 days on test, we would have had a lighter pig, so about 30 odd pounds lighter body weight, big impact on carcass. If you use the same base price, this would have been $17 less a pig, but they ate less because they were because they didn't eat as much over the test period. So that would have equated to about $12.85 due to the PRRS cost. But this price is probably a lot higher if you take into consideration any penalties for lighter carcasses and also medication. So I think it has big implications whether if you can feed your pigs out to get their body weight up to the right place, it may be cheaper than just trying to get everything out at once. So going into what Fitz alluded to, what is the metabolic cost of disease? And this is one of the questions that's been intriguing me for the last couple of years. When we think about our disease costs, we probably need to think of two things. One is the energy cost That is, what does it cost from an energy standpoint, in other words, ATP or heat production to run the immune system, to clear nitrogen, to change basal metabolic rate or have a febrile response. And the other aspect we need to consider is what are the amino acid costs? In other words, what does the needs of the animal to synthesize new immune cells, immune cell components? Also, amino acids, we sometimes forget, are actually going to be a major energy source when they feed into gluconeogenesis. So one of the assumptions that I've been working on from the immune standpoint, I've been following a lot of work out of Ireland from Luke O'Neill's lab, where he's actually trying to understand the metabolic consequences of an immune system challenge in T cells and B cells. And he talks a lot about this metabolic shift. So if we have the ability for an immune cell or an animal to actually shift towards glycolytic metabolism, away from oxidative metabolism, it seems to have a better resolution of the immune response in T cells and B cells. Due to the fact that it takes a shorter time to generate ATP through glycolysis than what it does through the oxidative phosphorylation, the Krebs cycle, TCA cycle, and oxidative phosphorylation. Also, if we have reduced feed intake, we have an increase in gluconeogenesis, because glucose is the primary fuel source for the immune system and immune response. Therefore, one of the reasons why we're seeing a big suppression in lean tissue is that we have a lot more amino acids being diverted towards gluconeogenesis and energy production than what we do towards lean growth. And then also there's been work out of Case DeLange's lab in Canada and others that have shown sulfur amino acids seem to be also important for the immune response. And whether that's due to the fact that they're involved in glutathione and oxidative or antioxidant proteins is up for debate. So on these lines, we've started looking at glucose insulin pathways within our pigs. And this is at 21 days, so 3 weeks in our PRRS naive and PRRS positive pigs. We see no difference in blood glucose in our pigs. Remember, these pigs have got a reduction in feed intake at this point in time, so they're naturally trying to maintain blood glucose levels, which makes sense, because they're trying to provide glucose to the peripheral tissues to support an immune response. But they're doing this under reduced insulin, therefore we have a higher or lower insulin to glucose ratio, which will indicate an insulin sensitivity due to a PRRS challenge. We've got some other data in some other disease models that actually shows in muscle there is actually a shift away from oxidative metabolism towards glycolytic metabolism that also would favour this. So the pig is doing everything it can to actually favour and maintain blood glucose. And it's doing this at the cost of lean tissue. In another earlier study that we've done, we looked at the metabolic analysis of some pig serum, and these pigs were all challenged with PRRS over a 56-day period. And I just really want to highlight the fact that our red and blue bars are just pigs that have different growth rates through a PRRS challenge. Fitz alluded to that some pigs seem to grow better through a PRRS challenge than others. All these pigs were PRRS challenged at the same time, and this is some work that has been done with collaboration with Jack Odell down at North Carolina State. What we can see here is that there seems to be some separation in glucose, citrate, lactate with regard to how these pigs grow through. So pigs that are able to maintain blood glucose seem to have better growth rates, and pigs that seem to struggle have lower growth rates. And this is some data we're just finalising right now. There's also differences in lactate, which would indicate differences in the Curie cycle, and citrate would indicate differences in TCA cycle. So in finishing up, what this data is starting to show us is that pigs that poor growth responding pigs to a PRRS challenge have higher blood glycerol, urea and lactate, lower blood glucose, pyruvate and citrate. And the pigs that seem to be able to regulate their metabolism or have a metabolic shift away from oxidative metabolism towards glycolytic metabolism, in other words, to favour glucose, seem to handle the immune challenge better. And this is also one reason why we're seeing a big hit on our lean accretion, because we have amino acids being mobilised for gluconeogenesis purposes. So really what it comes down to, why does this all matter? If we're thinking about how to feed a sick pig, we need to understand metabolically what does the pig actually need. And so I'm throwing out the idea, if people want to ever listen to me talk, is that if we can feed a pig a high glucose or a gluconeogenic substrate type diet, we should be preserving lean tissue accretion. And this is just a hypothesis that I want to test, and I want everyone else to prove it right or wrong as well, is that if we can provide the substrates that the pig needs for its metabolism, i.e. can we provide gluconeogenic substrates, whether we're talking about glutamine, glycerol, for instance. Fitz was talking about soybean meal. One reason is soybeans got a really nice amino acid profile that may be preferencing gluconeogenic substrates. Therefore, also glucose. If we can provide the pig with those substrates during the critical time, we should be preventing that loss of lean tissue, at least preserving lean tissue, and hopefully we can feed the pig during that period of time. So Dr. Pullman asked us, we talked about some key areas of opportunities he'd like to discuss, and this is some that I'd like to address in the future, is what happens if we can maintain appetite when these pigs are going through an immune challenge? Can we actually prevent a lot of the losses in lean tissue that pigs already put the energy into depositing? Or does it kill the pig, like it has in rodent studies if you force feed rodents that are sick? Can we lower the energetic cost of the disease? In other words, can we actually give the pig the energy it needs from exogenous sources, therefore it's not taking the hit off lean tissue? The other thing I want to stress is that in our nutritional strategies, we do not want to mitigate the immune response. We want the pig to have the immune response, but we want to resolve it as fast as we can without taking the hit on lean tissue. And then this provides opportunities and also challenges. Is there any reason why we should be feeding complex diets or expensive diets when pigs are sick if they've got poor feed intake and poor digestibility? It may be actually pointless. So do we just let the pig get over the challenge and then find the best time to come in once it's actually gone through or resolved this actual critical part of the immune challenge? But then I put compensated growth here because I still don't know whether it exists or not, but this actually has implications for feeding pigs at the back end once they get over the challenge.